In this lecture, we are going to see the topic NP complete problem. In the last class, we saw about P problem and NP problems. Now, we are going to see what is NP complete problem and NP hard problem. So, let us start with class P and class NP problems. Already we know class P problem is nothing but which can be solved in a polynomial time. And the examples for polynomial time are order of n square, order of n cube, order of 1 and order of n log n. And examples for non-polynomial times are order of 2 power n, order of n power n and order of n factorial. So these are the examples for non-polynomial time. So what is class NP? This is a problem which can be solved in a polynomial time. Within a stipulated time, we can get the solution for a particular problem. That is P problem. So what is NP problem? Which consists of set of problems that could be solved by NP algorithms, non-deterministic algorithms. So NP is nothing but it does not mean that non-polynomial. It means that non-deterministic polynomial. So the problems in NP also we can solve in polynomial time in non-deterministic Turing machine. That's why the name given as NP problem. So here the notable point is NP does not mean that non-polynomial. This is non-deterministic polynomial time. That is non-deterministic Turing machine. So what is NP complete? So we know what is P and what is NP. So what is NP complete and what is NP hard? So here consider the problem name is capital B. So a problem B is said to be NP complete if and only if the following two properties or conditions should be satisfied by a given problem. The first property or condition is capital B. Capital B is nothing but a given problem which belongs to NP. So the given problem belongs to NP problem. That is the first property. So the second property is for all problems capital A is under problem which is also belongs to NP. So here A belongs to A less than or equal to B, which means the problem A can be smaller or easier than the another problem capital B. From this for all the problem capital A belongs to, also belongs to NP, that is non-deterministic polynomial type. So these are the two properties. So if one given problem satisfied the given two properties, then that particular problem B is said to be NP complete. So what is NP hard? If the given problem satisfied only the second property, then that problem is called as NP hard. So NP complete means a given problem should satisfy the given two property, then the problem is said to be NP complete. If the given problem satisfied only the second property, then that problem is called as NP hard. So from this, there is no polynomial time algorithm to be discovered for an NP complete problem, and also there is no one has ever proven that no polynomial time algorithm can exist for any NP complete. So this is the definition of NP complete and NP hard. So the language is said to be NP complete if the particular language belongs to NP, and the second property is for all other L dash is also belongs to NP. So here L and L dash is a complement with each other. So a given language belongs to NP, and other than the given language, that is L dash, which also belongs to NP. So if the given language L satisfied the given two property 1 and 2, then the language is said to be NP complete. So what is NP hard? The given language L is NP hard if the language L dash also belongs to NP. L dash is the complement of L. So the given language satisfies only the second property, then the language is called as NP hard. If the language satisfied the given two properties, then that language is called as NP complete. So what is tractable and intractable problems? The problems in P, class P, are also called as tractable problems. So what is intractable or unsolvable or undecidable? The problems not in class P are called as intractable or unsolvable problems. So intractable means it can be solved in reasonable time only for some certain type of inputs or for small inputs only. So some of the examples for NP complete problem. This is the definition of NP complete problem. Already we know the definition of NP complete problem. So there are 6 examples, some of the examples for NP complete problem. The first example is CNF satisfiability problem. Second one is clique problem. Third one is vertex cover problem, subset sum problem, Hamiltonian cycle problem, traveling salesman problem. So these are the 6 example problems for NP complete problem. We will see one by one. We'll start with satisfiability problem. So what is CNF? The expansion for this is conjunctive normal form. So it is nothing but the form having the logical expressions with the logical connectivities are and not, and having this type symbol, and or having that kind of symbol, and not having this type of symbol. So the given CNF can be expressed as the given format like C1 and C2 and up to it goes to C suffix n of the sub expressions of Ci. So here Ci is disjunction of the given literal simple values. So consider the example statement like given the name is 1, x1 or not x2 or not x3. This whole value x1 not x2 not x3 called as the class. So the class only having the OR operator, and the second class value is not x1 x2 x3. So these having the operator logical connectivities are OR value OR, and the third class value is x1 or x2 or x3. So here there are 3 classes value that can be connected with the AND operator, and within that class values they are having the logical connectivities are OR operator. So second example is clique problem. So what is the clique? So the clique is an undirected graph. We know what is graph. So graph is equal to V comma E. Here V is vertex and E is edges. So the vertex are connected with some edge values. So the clique problem is used to finding the maximum size value in a given graph. So the clique have the definition like G comma K. Here G is a graph with the clique value of size is capital K. So G is graph and K is clique value, that is indicating the maximum size in a given graph. So consider this is the graph. There are 6 vertex A, B, C, D, E, A, B, C, D, E, F. There are 6 vertex, and that vertex pair, each and every pair connected by some edge value. So here the solution for this problem is B, C, E, F. The maximum size of the given value is 4, because B is 1, C2, E3, F4. So the maximum value is 4. So how we can get the solution like P, C, E, F? The value is 4. So here the vertex B, C, E, F forms a clique where each pair of vertex is connected by an edge in E. Consider the value, the vertex B. Here B is connected with C and B is connected with E, B is connected with F, and C, considering C is connected with B and C is connected with E, and next one is E is connected with C and E is connected with F. Last one is F, and F is connected with B, F is connected with E. So there are 4 the 4 edge connected or form a clique. So the here the maximum size value of clique is 4. So B, C, E, F, and the vertex B is connected with A and C, and C is connected with B, D, E. E is connected with A, C, F, and F is connected with E, B, D. So the every pair of the given vertex is connected by some edge value of E. So the third example is vertex cover problem. The vertex cover problem is an undirected graph. So G is equal to V comma E. It is a subset of V dash of V, because V is vertex. The subset of vertex having V dash value, such that the condition here is u comma v. The edge value is u comma v. So here the u in either v dash or v in v dash, any one of the edge having the value in v dash, or both having the value in v dash. V dash is the subset of given vertex v. So the vertex cover problem is used to find out the maximum size in a given undirected graph, right? So the vertex cover is a set of vertex which covers all the edges. So here this is an example graph. There are 6 vertex, 1 2 3 4 5 and 6. So here the maximum value vertex 6 2 5 6. The meaning of this problem is, here each and every vertex have to connected with all the vertex, so the sum of the which covers all the edges in the given graph. Consider the vertex cover value here is 2 comma 5 comma 6. So here the vertex 2 cover 1 comma 2. 2 is connected with 1, so we can write 1 comma 2, and also 2 is connected with 4, so we can write the second pair 2 comma 4. And the vertex 2 is connected with the edge vertex 3, so the third pair is 2 comma 3. So the single vertex 2 can be connected with 1 4 3. So we can write the pair like 1 comma 2 2 comma 4 and 2 comma 3. So the single vertex 2 cover at most 3 vertex in a given graph. So other than this vertex, the given graph having the vertex value 5 and 6 only. So we can write it as 5 comma 6. So for 5, the vertex pair is 4 comma 5, because 5 is connected with 4, so we can write it as 4 comma 5. And last one is 6. Here 3 is connected with 6. 6 is connected with 3, so we can write it as 3 comma 6. So the main aim is the each and every pair having connected with all the vertex in a given graph. So this is the aim of the vertex cover problem. So the name itself, it should be cover all the vertex in the minimum size, right? Sorry, maximum size. So the real-time application of this vertex cover problem is the placing ATM machine in a city, so that the minimum number of ATMs are placed to cover majority people. So this is a real-time application for vertex cover problem. So the next one is unsolvable or undecidable problem. So the example for this unsolvable or undecidable problem is halting problem. Already we saw in the 5th unit beginning itself, so refer that. And Hamiltonian cycle problem. So consider the directed graph, that is G is equal to V comma E. V is vertex, E is edge. So this Hamiltonian cycle or circuit, which is used to determine or find out the simple cycle that contains each vertex in V. The main condition or property here is each vertex can be visited only once only. Consider the two examples. The first one is Hamiltonian cycle or circuit. The second one is not Hamiltonian cycle or circuit, because consider the first circuit. Here there are 5 vertex, right? So you can consider the first one is 1, and so consider this is 1, and this is 2, this is 3, and this is 4, and this is the vertex number 5. Consider this. Here we can connect 1 to 4, right? And also we can connect 1 to 5. Next we can connect 2 to 3 and 3 to 4, either 2 to 5. So here all the vertex can be visited only once. So this is an example for Hamiltonian circuit. But you can take the second circuit which is not Hamiltonian, because here consider this is 1 and this is 2, this is 3, this is 4, this is 5, means here you can visit the vertex more than once, because 1 to 5, and after 2 to 5 to 2, and 2 to 4. So here already 1 3 5, 1 and 5 is connected by 3, but again the edge going from 2 to 5 also getting the edge value is 3. So here the vertex 3 has been visited more than once. So this is not a Hamiltonian cycle or circuit. So the main aim of this cycle or circuit is have to be it is used to find out the simple cycle, but each vertex in the given graph has visited only once. This is the main aim of this Hamiltonian cycle problem. So next one is intractable problems. So it can be classified into NP and NP complete and NP hard problems. So these are the example for intractable problems. So the main point in intractable or tractable and NP complete, NP hard is reduction one, because we can say that the reduction is the easiest way to reducing one problem into another problem. Consider there are two problems, one is capital A and second one is capital B. If the first problem capital A is easier than capital B, second problem, then we can write it as A less than or equal to B, because here A can be solved easily rather than capital B, so it can be write it as A less than or equal to B. And also we can solve the first problem A by using some algorithm. That algorithm also used to solve the second problem capital B, because A is easier than B. So some algorithm to be used for capital B to get some solution. The same algorithm can also be used for getting solution from capital A. So this is the concept of reduction. So here the problem A can be reduced to problem B by getting the input alpha and B. So finally the result is either yes or no. So what is polynomial reduction? Consider the two given problems capital A and capital B. Here we can say that the given problem capital A is polynomially reducible to capital B. It can be write it as capital A less than or equal to P, that is polynomial, and capital B. So the same one here, if the problem A can be polynomial reducible to capital B, then it can be write it as A less than or equal to B, and B belongs to P, then capital A belongs to P, right? If capital A does not belongs to P, then capital B also does not belongs to capital B. This is the main property of polynomial reduction. So how to prove the polynomial time? So the first one is polynomial time algorithm to decide the solution for the first problem capital A. So the second one is polynomial time algorithm to be used to get the solution for capital B. Here we can use polynomial time reduction algorithm to translate or reduce from A into B. We can run the already known polynomial time algorithm for capital B. So use the answer for capital B as the answer for capital A, because we can reduce the problem A into B. So after getting the solution or result from capital B, that same can be used for the first problem capital A. So P and this is an example for P and NP complete problem, and shortest, we can find the shortest path in the simple graph, and it get the solution in a given polynomial time. So this is an example for P complete problem. And if we can find the longest path in a given graph, then that is an example for NP complete problem. So the first one is example for P complete problem, and second one is an example for NP complete problem. So the first one also example for P problem, second one is an example for NP complete problem. Already we saw the Hamiltonian cycle as an example of NP complete problem in the previous slides. So the first one is Euler-Tour. So that is an example for P complete problem. So it is a directed graph which is used to find the cycle that traverses each edge of the given graph exactly once, but it can visit the vertex multiple times, right? Consider the given graph, there are 5 vertex, means you can visit the 5 vertex at many times, multiple times, but you can traverse in each edge of the particular vertex at least at once only. So that is the main difference between Hamiltonian and Euler-Tour. So Euler-Tour is an example for P problem, and Hamiltonian is an example for NP complete problem. So already we saw that satisfiability problem. So here that classes are here 4 classes: x1 not x2, x3 not x4. There are 4 classes. So CNF satisfiability problem, conjugative normal form. So it can be included as an AND of expressions, because each and there are 3 classes. The arrow mark indicates x1. Each class contains only R of the values and their complements. So the 3 classes are connected with the AND expressions, AND operator, and each class having OR operator. x1 or x2, x1 or not x2, not x1 or not x2. So each and every class having the OR operator within that, but the 3 classes connected with the AND connectivity. So what is 3 CNF satisfiability problem? Which means the CNF having 3 classes. If the given CNF satisfiability problem having 3 classes, then that is called as 3 CNF. The main point here is 3 CNF is an example for NP complete problem, but 2 CNF is an example for P complete problem. P problem. So click problem, already we saw that it is a subset of given vertex in V, which can connected to all each edge by each other edge by in a given graph. It is a complete subgraph. So click is a complete subgraph. In that subgraph, complete subgraph means all the vertex in the subgraph connected with all the vertex in the given subgraph also. So this is an example for click problem. So this is an click verifier. The given problem is click or not. So this is an NP naming conversion. So we know what is NP complete and what is NP hard. So NP complete means the problems that are complete in NP, and it is most difficult to solve. The problem can be very difficult to solve in NP. And NP hard stands for at least as hard as NP, but not necessarily in NP, because we know that there are 2 properties to be satisfied by NP complete problem. In those property, if the given problem satisfied only the second property, then that is called as NP hard. That's why they are given like, but not necessarily in NP. So what is NP easy? Stands for at most as hard as NP, but not necessarily in NP. Last one is NP equivalent, which means it's equally difficult as NP, but not necessarily in NP. So the first one, NP complete, should only satisfy the given 2 properties. The below 3, NP hard, NP easy and NP equivalent, should not necessarily in NP, which means it should not satisfy the first property. If the given problem satisfies the second property, then that problem can be called as NP hard, NP easy and NP equivalent. So these are the examples for NP complete and NP hard problem. Hamiltonian path is an example for NP complete problem, and also the example traveling salesman problem is an example for NP problems. So Hamiltonian is an example for NP complete, and traveling is an example for NP hard. So from this lecture you can get clear knowledge about what is NP, what is P, and what is NP complete problem, and what is NP hard, what is the definition of NP complete and NP hard, and examples for tractable and intractable problem, what is click, what is vertex cover problem, what is Hamiltonian cycle,